Welcome. This is a time series analysis course. My name is Nicola da Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is a multivariate time series analysis. On this lesson, I'll introduce another concept that applies to an extension of the VAR model, specifically cointegration. Thus, from the previous lesson, from generalizing using the VAR-X model, which allows for seasonality and trend, and structured VAR model, which allows for contemporaneous relationships, now the generalization allows for non-stationary VAR model, which can be dealt using differencing approach. In a different lecture, we learn about an approach for dealing with non-stationary time series, specifically differencing the time series. This concept applies generally to both univariate and multivariate time series and is formally defined as integration. To be more specific, if the d-order difference of a time series yt is stationary, we define that yt is integrated of order d, or more concisely, write yt tilde I of d. I of d is an indication, is a definition of integrated time series of order d. If d is equal to 0, then the time series yt is stationary. Thus, we do not need to take any difference to make it stationary. When d is equal to 1, then only a order equal to 1 difference is sufficient to obtain a stationary time series. While integration means taking a d-order difference of the time series, co-integration means taking a linear transformation beta of the vector time series yt, where yt is a multivariate time series such that the resulting linear combination is a stationary time series. The linear combination beta transpose yt is often motivated by economic theory and referred to as a long-run equilibrium relationship. It's important to know that the vector beta is not unique in making the linear combination of the multivariate time series stationary. We can multiply this vector with any value, with any constant, which will result in a rescaled time series. This will not change the stationarity property of the linear combination beta transpose yt. Thus, we need to impose a constraint on the element of the vector beta in order to have a unique linear combination. This is called normalization. A typical normalization is to consider a vector of the coefficients in which the first value in a vector is 1, as the vector beta provided on the slide. Using this vector beta, if we multiply y beta transpose with yt, we'll get y1t minus beta 2 y2t up to beta n ynt equal to ut, or the equation provided on a slide where y1t is equal to this linear combination of beta and contemporaneous values of the time series plus ut. Ut is a cointegrated residual. Ut is a stationary time series. For an n-dimensional multivariate time series, we can identify up to n-1 such cointegration relationships. For example, if we consider a trivariate time series with n equal to 3, there may be two different cointegrating vectors, beta 1 and beta 2, such that the linear combinations using these vectors result in stationary time series. These two vectors are linearly independent, otherwise they will lead to the same cointegrated relationship. The matrix B, with each row corresponding to one cointegrating vector, is called the cointegrating basis. Two important properties are as follows. One is that both vectors need to be normalized to be unique, as discussed on the previous slide. Second property is that any linear combination of the two vectors leads to a cointegrating vector. This is why B is called cointegrating basis, since the two vectors are the basis of any other cointegrating vector. Let's now consider a multivariate time series with n time series, which is of integration of order 1, meaning that linear combinations are sufficient, that one order or linear combinations are sufficient in transforming the multivariate time series into a stationary time series. Similarly, as for n equal to 3, we can identify up to n-1 different unique cointegrating vectors, which will form the cointegrating basis as in the previous slide. Cointegration hypothesis tests cover two situations. One is that there is at most one cointegrating vector. The other is that there are multiple cointegrating relationships. These two approaches have been introduced in the references provided on the slide. Let's take a closer look at these approaches. First, let's define the hypothesis. In testing for cointegration, the new hypothesis is that of cointegrated multivariate time series, assuming an integrated time series of order 1, and the alternative is that the multivariate time series is stationary. Note that this is not a test of stationarity, it is a test of cointegration. The general approach proposed by Engel and Granger is that of two-step method. First, form the cointegration vectors and test whether the residual time series is stationary, thus employing a test for stationarity. There are two situations here. One is when the cointegrating vector is known. The other is when it is not known. When the cointegrating vector is not known, it can be estimated from the data, assuming that it's cointegrated. To note, when the basis is not known, some normalization assumption must be made to uniquely identify it. We can expand the idea of cointegration to VAR models. Let's consider the classic VAR model with a deterministic component. VAR is stable if and only if there are no roots of the VAR polynomial in the unit circle. Moreover, stability implies stationarity, but not the opposite. Stationarity condition is less restrictive. A VAR is stationary if there are no roots in modulus that are exactly on the unit circle. If there are roots on the unit circle, then some or all of the time series in YT are integrated of order 1, and they may be also cointegrated. If YT is cointegrated, then the VAR representation is not the most suitable representation for analysis because the cointegrating relationships are not explicitly apparent. The cointegrating relationships become apparent if the VAR is transformed to the vector error correction model, abbreviated as VEC-M. VEC-M is particularly of interest in the interpretation of the relationships between the time series by introducing concepts such as long-term relationship between variables and the associated concept of error correction, whereas one studies how deviations from the long run are corrected. The VEC-M is described on the slide. In this definition, the matrix pi is 1 minus the sum of the pi I matrices in the original VAR model. This first component, pi times yt minus 1, is the only part that can be integrated of order 1. All other components are differences of the lags t minus 1 to t minus p plus 1 and hence are stationary. To ensure that the model is identifiable, we need to assume conditions on gamma, k, and pi matrices as provided on the slide. I will not explain further on this model since it requires more advanced modeling. Its application is more relevant to understanding relationships between time series rather than forecasting. In summary, in this last lesson, I introduced an extension of the VAR model which allows to model multivariate non-stationary time series. Thank you.